So what we're going to do in this video is make truth tables for the following formulas. One of them is the logical expression not P or Q. The other is the logical expression is logical AND of S or G and not S or not G. So if this all sounds quite unfamiliar to you, just as a refresher, I'm hoping you have some familiarity with sentential logic, but just to go through the basics real quick. We have statements called propositions. So P, Q, S, and what was the other one? G. In the above examples, these are all examples of things we call propositions. Propositions are statements which have either which have a truth value, which is either true, which we write as T, or false, which we write as capital F. I didn't need to write falses. Okay, so these are propositions. We can combine different statements, or we can combine different propositions using logical connectives such as not, or, and AND. So let's go through what each of these mean really quickly. Again, hoping you have some familiarity with these. So P, let's say, is a proposition. It can take on either F, the truth value F, or it can take on the truth value T. So if you negate it, what you're gonna get is negation of P is defined as being the opposite of P. So whenever P is false, negation of P is going to take on the value true, and whenever P is true, it's going to take on the value false. Let's see what happens when you try to combine two propositions with a logical connector such as OR. So let's draw all the possible combinations of truth values. Again, since we have two propositions here, notice we're going to have four combinations. Why is that? Because two combinations for P times two combinations for Q, because P can be true or false, and Q can be true and false. Similarly, if we have three statements, P, Q, and R, we're going to have 8 possible combinations, which is 2 for P, 2 for Q, and 2 for R. So if this doesn't make too much sense, I'm going to demonstrate what I exactly mean by this. The first combination that we can have of P and Q's truth values taken together is both of them are false. Another possible scenario is P is false but Q is true. Another possible scenario is P is true but Q is false. And the last possible scenario, the only remaining possible scenario, is both P and Q are true. So what P or Q says is let me just write P or Q separately over here. So you have P or Q, these are the possible values. This is the combined proposition, which is the logical OR operator, or like logical OR of P and Q. I shouldn't say P and Q because then it's confusing with the logical operator and. I just mean the operation P or Q. And just as a refresher, this will be true when either P is true or Q is true or both are true. So it's not like only one of them needs to be true. You can have both P and Q to be true at the same time. So this will be true when Q is true, when either of these is true, or both of them are true. So I hope that wasn't too confusing. Let me show what I mean. So when in the second row, if you see, P is false but Q is true, so P or Q will be true. P is true in this third row, P is true and Q is false. So again, P or Q is going to be true because at least one of them is true. And in the last and final row, we have P and Q as both being true. The requirement is just that at least one of them needs to be true. If both of them are true, great. That's also fine. We're going to have T there as in true. However, with P or Q, in the first line or first row, we have both of them false. So since this requires that at least one of the propositions be true, but in this first combination, we have both of them as being false. So just going to put oops, I didn't mean to erase that. We're going to put both of them as being, since both of them are false, we're going to put the result of the operation as being false here. Really quickly, what P and Q means is both of them need to be true. Both P and Q need to be true. So this first thing is going to be false because we have, if there is even one false out of P and Q, then the entire operation is going to be false. So again, false here because P is false here because Q is false, and finally we have T, both of them true in the last row. So finally P and Q is going to be true. So these are the truth tables for P or Q and P and Q. So let's now look at how to make more complicated expressions. Let's go and try to draw what negation P or Q is going to look like. So we're going to have negation P or Q. So first let's write down all the values of P and Q, all possible values, FFTT. I am writing it this way, this might be confusing, but you get used to it. So once you start writing down all the possibilities like FF, FT, TF, and TT, you sort of start to remember, okay, there's a certain pattern to it. I write two Fs at once and two Ts at once for P, and then for Q, I cycle through them one by one, in the sense that for both Fs, I can have either an F or T for Q, and for both Ts, I can have either an F or T for Q. I probably didn't make that very clear. I probably confused you even more, but just don't worry about it. Try to write the combinations explicitly for the first few times, and then once you get used to it, you should be able to like write them down one column at a time like I did. You can sort of memorize the pattern, and you can be sure that these cover all possible combinations because they're unique combinations, and they are 4, and we know that these can only have 4 combinations. So let's see what not P is going to look like, because we need to find not P or Q. So we need the value of not P or the truth values of not P, all the possible ones, and all the possible truth values of Q. We already have that. So not P is going to be T, T, F, F. Why is that? Because P is F here, so not P is going to be opposite, which is true. F is going to be, not P is going to be true. And when it's T, not P is going to be F. And it's T, not P is going to be F. Cool. What about not P or Q? So we have to do the OR of these two propositions over here. So not P or Q. And again, remember the OR is commutative because it doesn't matter the order in which you're ORing, if I should say that. In the order of operation doesn't matter because you're only looking at if at least one of the two propositions is true, and that is clearly independent of which proposition comes first in the expression. So in other words, A or B is the same as B or A, where A and B are any two propositions. Now, what's not P or Q? Not P or Q is going to be, let's see, in the first row we have at least one of them is true, so true here. Let me maybe use a different color to note that this is the final truth table column that we're looking for. Here again we're gonna have, let me get rid of this, we have both of them as true, so again great, we just need one of them to be true. If both of them are true, that's fine. In this row however, both of them are false, so we don't, it's not the case that at least one of not P and Q are true. In other words, both of them are false in this row, so the OR is also going to be false. Finally, in this row, we have Q is true, so that makes the whole expression true. So this is the desired truth table for the first example, which is not P or Q. Let's take a look at the next exercise, which is, or like the second part of this exercise, which is S or G and not S or not G. So that sounds like a mouthful. Let's start by just, there's only two expressions really. It's S and G, so yeah. S and G, we can write down FF, sorry, I should have written FF, FT, TF, and TT, and you can see what I mean when I say you can just write them down one column at a time, FFTT and FTFT. You get sort of used to this pattern, that's fine. Let's write down what S or G. The first part of this expression is S or G, so let's see what the values of that are going to be. This is pretty straightforward. We already drew the truth table for, oops, my bad. We already drew the truth table for OR, so we know it's going to be FTTT. Once again, to see why this is, both of them are false here, so the OR is also going to be false. Oh, I didn't mean to do that. Here at least one of them is true, and both of them are true. So in the second, third, and fourth rows, we're gonna have true for the logical connective OR. And now we want to see what's not S or not G. So before we do that, let's see what not S is. Not S is going to be just, again, I'm gonna quickly do this, TTFF, because it's the opposite of S. Not G is going to be TFTF because it's opposite of G. You can verify that, pause the video and verify that. And not S or not G, it's just going to be the OR of these two. So let's write that down real quick. I meant to say G. That is going to be, we're going to have the OR of these two, which is T because both of them are true here. T because not S is true. Again T because not G is true, but F because both not S and not G are false here, so that's going to be S. Remember, this is an OR. Now we finally have to the AND of S or G and not S or not G. So in other words, let's call this proposition P1, this entire thing, and let's call this entire thing proposition P2. So we have to find P1 and P2. The way we do that is essentially just take both of these columns and do the regular AND operation, the way we're used to it. Since this is a bit of a longer proposition to write, I'm just going to call this entire thing P, so I can just write the column as P rather than having to write the whole thing. And I know that P is going to be equal to P1 and P2, so let's write that down. P1 is F here, so the AND becomes F, because remember the AND requires both propositions to be true in that case. Since P1 and P2 are both true in this case, we're going to have true for the AND here. P1 and P2 are again both true, so we're going to have true here, and P1 is true but P2 is false, so this is going to be false. So this is the truth table for P, which is nothing but S or G and not S or not G.